Welcome to the Inter-Integrated Circuit, I²C chapter of the HT32 MCU basic tutorial. This tutorial will introduce to you the HT32 MCU I²C function. We'll introduce this function from 6 aspects. Introduction. Communication protocol. Data transmission. Features. Example. An I²C API list. Introduction. I²C is a serial communication bus developed by Philips in the 1980s. It is commonly used for transmitting data between microcontrollers and various peripheral devices, such as sensors, displays, and EEPROM. The I²C uses 2 lines for data transfer, with the communication initiated by the master controller to the slave device. All devices connected to the bus drive signals in open drain mode, requiring external pull-up resistors to maintain the signal lines at a high level. These resistors are typically located close to the master. This architecture allows multiple devices to share the same bus and enables bidirectional communication in a multi-master and multi-slave configuration. This reduces the number of connection lines, thus simplifying the circuit design. The SDA and SCL lines are the 2 I²C serial lines. SCL is the serial clock line that provides the clock signal from the master to synchronize data transfer. SDA is the serial data line and is used for data transfer. The I²C bus uses an open drain design, which requires pull-up resistors to maintain the serial lines at a high level. In the I²C communication, the master device controls the SCL line and initializes a data transfer. All data transfer synchronization relies on this clock. At the start of communication, the master determines that the data transfer direction is read or write. For example, write the data to slave A. When slave A receives the master write a signal, it will respond with an ACK signal. Once the master receives the ACK signal, it will transmit the data. Read operation is similar. For example, when slave B receives the master read B signal, it will respond with an ACK and then write the data to the master. Communication protocol. A master device can initialize a transfer by sending a start signal and terminate the transfer with a stop signal. A start signal is usually referred to as the S bit, which is defined as a high to low transition on the SDA line while the SCL line is high. A stop signal is usually referred to as the P bit, which is defined as a low to high transition on the SDA line while the SCL line is high. During data transfer, the data on the SDA line must be stable during the high period of the SCL clock and the level state cannot be changed. The SDA data state can only be changed when the clock signal on the SCL line is in a low state, otherwise, a bus error event occurs. If an unpredictable start or stop condition occurs when the data is being transferred, it will be considered as a bus error. In the I²C communication protocol, an acknowledge ACK and a not acknowledge an ACK are important signals in communication between master and slave, primarily used to indicate whether the data has been successfully received. When the receiver has received an 8-bit address or data, the receiver will respond with an ACK. Then the receiver, whether master or slave, will pull the SDA line low on the 9th clock cycle. If the data is received incorrectly, or if the receiver does not wish to receive any more data, it will respond with ANACK. This means that the SDA line will not be pulled low on the 9th clock cycle. Once the slave device address has been matched, the master will transmit or receive the data to the slave according to the transfer direction specified by the RW bit. Each byte is followed by an ACK bit or ANACK on the 9th SCL clock. When the master acts as the transmitter, if the slave has received the data, the master will receive an ACK from the slave. Conversely, if no response is received, this is interpreted as an ACK. When the slave acts as the transmitter, if the master has received the data transmitted from the slave and wishes to continue receiving data, the slave will receive an ACK from the master. If the master device sends an ACK to the slave device will release the SDA line for the master device to generate a stop signal to terminate the transfer. The I²C interface starts to transfer data after the master device has sent the address and has received an ACK from the targeted slave device. Here, take a write operation as an example. The address frame is sent just after the start signal by the master device. The RW bit defines the direction of the data transfer. Read is 1, write is 0. If the slave address matches the address frame, it sends back an ACK. If not, it sends back an ACK. The I²C usually uses a 7-bit addressing mode, which only supports 128 devices. To prevent address clashes, a 10-bit addressing mode is also available, which increases the available address range about 8 times. In the 10-bit mode, the address requires 2 bytes, which has one more header byte than the 7-bit mode. The first byte is composed of a leading 11110, 10th and 9th bits of the slave address and a RW bit. The second byte is the remaining 8-bit address of the slave device. In the read mode, the header byte must be transmitted again, and the RW bit is set to read. A master may start a transfer only when the I²C bus line is in the idle mode and both the SDA and SCL lines are at a high level. If 2 or more masters generate a start signal at approximately the same time, an arbitration procedure will occur. As shown in the figure, if 2 devices generate a start signal simultaneously, they will both continuously transmit many bits on the SDA line until the low SDA state of device 2 overrides the high SDA state of device 1. At this time, device 1 will lose the arbitration and set the ARBLOS bit high, monitoring the bus in order to detect an I²C stop signal. Once the stop signal is detected, the device 1 which has lost the arbitration may try to access the bus again. Data transmission. The I²C module can operate in one of the following modes: master transmitter, master receiver, slave transmitter, slave receiver. In the master transmitter mode, after the master sends the start signal, the STA bit is set. This indicates that the start signal has been sent. The STA flag can be cleared by reading the I²CSR register. It must be cleared before transmitting the address frame. After the master receives the ACK, the ADRS flag is set. This indicates that the address frame has been sent by the master. The ADRS flag can be cleared by reading the I²CSR register. It must be cleared before transmitting the data frame. The data to be transmitted must be written into the TX buffer. This operation clears the TXDE bit. The TXDE bit indicates that the TX buffer is empty. After transmitting the last data byte, the TXDE bit is cleared automatically by hardware after setting the stop command. The master then transmits a stop signal. In the master receiver mode, once a data has been received by the master device, the RxDNE flag is set. The RxDNE bit indicates that the Rx buffer is not empty. If a new data byte is received before the Rx buffer data has been read out, the master will hold the SCL line at a logic low state. The master will only release the SCL line once the Rx buffer data has been read out, allowing the slave to continue transmitting data. After the last data byte has been received from the slave device, the master device will send an ACK signal to the slave device. Finally, the master transmits a stop signal to terminate the data transfer. In the slave transmitter mode, Before transmitting data, the slave must first write the data to the TX buffer. If the TX buffer is empty, the TXDE bit is set to 1, which results in the SCL line being held at a logic low state. Writing data into the TX buffer will clear the TXDE bit to start the data transfer. When the slave device receives an ACK signal, the RxN ACK bit is set. Writing 1 to the RxN ACK bit will clear the RxN ACK flag. The RxN ACK bit indicates that the NACK signal is received in the transmitter mode. When the slave receives a stop signal, the STO bit is set to indicate that the transfer is terminated. Reading the I²C register can clear the STO flag. In the slave receiver mode, once a data has been received by the slave device, the RxDNE flag is set. The RxDNE bit indicates that the Rx buffer is not empty. If a new data byte is received before the Rx buffer data has been read out, the slave will hold the SCL line at a logic low state. The slave will only release the SCL line once the Rx buffer data has been read out, allowing the master to continue transmitting data. When the slave receives a stop signal, the STO bit is set to indicate that the transfer is terminated. In the I²C communication, the SCL line is used to synchronize the clock signal. When the SCL line is holding at a logic low state, the I²C data transfer will be stopped. The conditions of holding SCL line in the table are categorized into two types, flag and event. When the I²C is in the transmitter mode and the data needs to be written to the TX buffer, the SCL line will be held at a low state until the TX buffer is not empty. When the slave receives a general call, the SCL line will be held at a low state until the status register is read. When the master sends an address and waits for an ACK signal from the slave, or when the I²C is addressed as the slave, the SCL line will be held at a low state until the status register is read. When the master sends a start signal, the SCL line will be held at a low state until the status register is read. The SCL line will be held at a low state until the data in the Rx buffer is read when the Rx buffer is full. No matter an address or data transfer process, once an ACK signal is received, the master will hold the SCL line at a low state until it terminates the data transfer or restarts a new transfer. After the last data byte has been received from the slave device, the master device will send an ACK signal to the slave device. Then the master will hold the SCL line at a low state until it terminates the data transfer or restarts a new transfer. Features. The HT32 I²C interface provides the address snoop function. The address snoop register, I²C ADDSR, is used to monitor the calling address on the I²C bus. Taking the address frame sent by the master with hex 01 as an example. Each calling address on the I²C bus will be stored in the I²C ADDSR register. Automatically, no matter if the I²C module operates as a master or a slave device. Even if the I²C device is not addressed. The HT32 I²C interface provides the address mask function, which can be used to ignore specific bits within the address frame sent from the master. When the unmasked bits and the address frame sent from the master are matched, an ACK will be returned. This function is only available in the slave mode. For example, the slave address is hex 50, masked address is hex 03. If an address which is sent by the master is equal to hex 50, hex 51, hex 52, or hex 53, the slave address will all be considered to be matched and the slave will return an ACK signal. In order to reduce the occurrence of I²C lockup problem due to the reception of erroneous clock source, a timeout function is provided. If the I²C bus clock source is not received for a certain timeout period, then a corresponding I²C timeout flag will be asserted. The I²C register is used to define the timeout counter preload value and the counter prescaler setting. The timeout counter will start to count down from the preloaded value if the ENTOUT bit is set to 1 and one of the following conditions occurs. First, the master sends a start signal. Second, the slave detects a start signal. Third, the RxBF, TXDE, RxDNE, RxNACK, GCS or ADRS flags are asserted. The RxBF indicates that the Rx buffer is full. The TXDE and RxDNE indicate that the TX buffer is empty, and the Rx buffer is not empty. The RxNACK indicates that the not acknowledged signal is received in the transmitter mode. The GCS indicates that a general call is received. The ADRS indicates that the address has been transmitted or matches. The timeout counter will stop counting when the ENTOUT bit is cleared. However, the counter will also stop counting when the conditions, listed as follows, occur. First, the slave is not addressed. Second, the slave detects a stop signal. Third, the master sends a stop signal. Fourth, the ARBLOS or BUSERR flags are asserted. The ARBLOS indicates that arbitration loss is detected. The BUSSERR indicates that bus error has occurred. The PDMA interface is integrated in the I²C module. The PDMA function is used to move data from the I²CDR register to a specified memory location, reducing the cost of moving data in the CPU. The PDMA function can be enabled by setting the TXDMAE or RxDMAE bit to 1 in the transmitter or receiver mode respectively. The DMANACK is used to confirm whether ANACK signal is sent. In the master receiver mode, if the DMANACK bit is set to 1 and the data has all been received and moved using the PDMA interface, ANACK signal will automatically be sent out to terminate the data transfer. Before configuring the PDMA, the I²C PDMA channel must first be confirmed. This can be found in the PDMA chapter of the user manual. For example, the HT32F52352 uses channels CH2 to CH5 as the PDMA channels for the I²C0 and I²C1 modules. For a more detailed description on the PDMA configurations, refer to the PDMA chapter. Example. Next, we will introduce the I²C configuration process using the 7-bit master and 7-bit slave example. 2 starter kit boards must be prepared before commencing. Here, we will use the ESK32-30501 as an example. First, connect the SDA and SCL pins on the 2 boards by connecting PA0 to PA0 and PA1 to PA1. Each line must be connected to a pull-up resistor ranging from 3.3 kΩ to 4.7 kΩ. The example shows a master sending data to a slave. After receiving data, the slave returns it to the master. If the received data is correct, LED 1 lights up. Otherwise, LED 2 lights up. The configuration process is introduced on the following page. The following will introduce the master configuration. First, configure the LEDs to show the transfer result. Before transfer, configure the I²C and AF I/O clock. Configure the IOs to I²C mode. Configure the master address, address format and clock speed, disable the acknowledge. Enable the I²C interface. The following will introduce the slave configuration. First, configure the LEDs to show the transfer result. Before transfer, configure the I²C and AF I/O clock. Configure the I/Os to I²C mode. Configure the slave address format, enable the acknowledge. Enable the I²C interface. Then configure the I²C master transmitter. Start a transfer, execute a write operation with the master transmitting the slave address. This involves transmitting a start signal and the address. Check whether the master has transmitted the start signal and address, and has received an acknowledgement. Then transmit the TX buffer data. Once data transfer is complete, send the stop signal. Wait for the bus to become idle, then exit the loop. Then configure the slave receiver. Check whether receives the matched address. Receive data and store it to the RX buffer. After receiving the data, wait for a stop signal. If the master requires to read back the data, the master receiver also needs to be configured. Start a transfer, execute a read operation with the master transmitting the slave address. This involves transmitting a start signal and the address. Check whether the master has transmitted the start signal and address, and has received an acknowledgement. Enable the acknowledgement function to indicate to the slave whether it should continue to receive data. Store the received data in the RX buffer. Disable the acknowledgement function before the last byte data transfer has been completed. Send the stop after the last data byte has been received. Send a stop signal to terminate the transfer. Wait for the bus to become idle, then exit the loop. Check that the data in the RX buffer and the TX buffer are the same. If they are, LED 1 will light up. Otherwise, LED 2 will light up. If the slave requires to send back the data to the master, the slave transmitter also needs to be configured. Check whether receives the matched address. Transmit the received data in the RX buffer. After transmitting the data, wait for an ACK signal from the master. Check whether the data in the RX buffer is correct. If yes, LED 1 will light up. Otherwise, LED 2 will light up. If the examples have been completed, both of the LED 1 on the starter kit boards will light up. I²C API List. This tutorial concludes with a list of the I²C API, along with their corresponding descriptions. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.